Okay, hello everyone. I'm Matt Bovel. I'm a first year PhD student here at TPFL, co-supervised by Martin Odarski and Viktor Kunchak. And I am working on precise types in Scala and especially type level operations. So I will explain what that is and what are the use cases for it in a minute. If you want to know exactly what I will be talking about, this is the outline. Don't worry, there is one item per slide, but it should not be that long, okay? So basically I will start with a recap about what kind of types we have in Scala and what we can do with it already today. Then I will show you a bit what I've been working on to be able to reason algebraically and abstractly about operations in types. I will show you a few examples. And then we will continue with a few examples on type level programmation with match types. And we will also finally implement ourselves two new compile time operations, because this is Compiler Academy, so the idea is to write a bit of code in the end. Okay? So let's start with the basis. I was talking about precise type. What is the most precise type we can think about? Well, it's a type where you already know the value. These are called literal types in Scala. And so, for example, if I have the constant free, I can say, well, it is a type that has at most one inhabitant, and it is the constant free. This is similar to what you will have in TypeScript, for example. So, of course, this is way more precise than int, which has like 2 to the power of 31 different possibilities. Here I know exactly the value at compile time. Same is true for booleans, same is true for string. Here you see I'm assigning this constant string Monday to a variable that has the type either Monday or Tuesday. This is not really idiomatic in Scala. You would use an enum. This is something you would see in TypeScript, for example, but that's for the demo. Okay, so that's already quite useful, and we will use this a lot in the presentation, but let me show you another kind of type, term references. So here, we also have a type inhabited by a single value. So if you think denators only, then it's a set with a single element, but we don't know yet what it will be, okay? So how do we encode that? Well, we reference a term somewhere in the program, and we say, I will assign to this variable exactly the value of this term, even if I don't know it yet, okay? So how do you type that in Scala? Well, you can have the precise type of the value a by writing a.type. And in this case, I can successfully assign a to c because a is known to have the value a.type. Okay? However, yes?
Are there any restrictions on where you can use .type?
Yes, you can only use them on what is called path. So basically, what is here should be stable. It should be known at compile time. So I could not use it on the result of a function, for example, or something like that. It's only a path, so it's either a variable, or a variable where I select something. Okay? And so here we see an error because I say that E must have exactly the type of A, so the value of A, and actually I assign B, which can be any integer, so it will be an error. The free question mark, is it clear for everyone? It's just when I'm talking about type and I'm not concerned about implementation, I use this, so basically it can be anything here, okay? Good. So you can use them in functions also. So here, for example, I say that in the function same, the parameter b, the argument that will be passed here, should have exactly the same type as a, okay? So if I pass 3 2 times, it will work. If I pass 3 and 4, I will have an error, okay? This is what we call a dependent parameter, and by extension, we call this a dependent method, okay? It's a method or a function where we have some the types of some arguments that are depending on previous arguments. Just slight heads up here to show you that it does not work exactly like the type parameters, okay? So here I'm really using the precise type of A directly, and it will be the most precise type possible, okay? If I had the type parameter, then this would work, because by type inference, I would infer that T is actually int, so I would take the common supertype of A and B, and then this would compile. So in general, in this presentation, and in general, I prefer to use dependent type because somehow they're a bit less powerful, okay? You can really think about them by means of substitution. So in this type, I will substitute this by the type I give A, and then I don't have to be concerned about type inference, about constraints, etc. Okay? Good. The last building block that we need, and this is the main theme of my presentation, are compile time operations. What are these? Well, these are some type applications, type aliases that are defined in the standard library. So here is an example. This represents the type of the addition of two integers. So the two arguments are upper bounded by int, and the result is upper bounded by int as well, okay? So I say this type will be a subtype of int, but I don't know exactly the subtype. If I just had that, it would not be super useful because I could never reduce it. So I could represent the type application of plus with two types, but I couldn't do anything with it. But Scala has special support for them in the compiler, such that it will automatically constant fold these type applications if the arguments are constant. So here is an example. I import this type plus, not to be confused with the term level plus, right? From the package scala.compiletime.ops. And then I can here define the type of the literal 2 plus 2, and the compiler will automatically fold this to 4 such that I can assign 4 to this. So right now it only works with constant types, literal types. If I had here n.type plus 2 or 2 plus n.type, this could not be reduced. Well, of course, what can you reduce it to? So I will talk a bit about it later. Good. Oh, yeah. The last building block we need is refinement types, because very often we will have these precise types as fields in an object. So here I will start with the classic example where we have a vector or list with a size that is known at compile time. So if I just type it like that, I know the size is an int. I don't know the precise size, right? But I can refine it using this syntax here and say, okay, here my value v will not only be a vector, but it will be a vector where I know that the field size has exactly the type 2. Okay? And then if I try to assign v.size to a value that has the type 2, it will work. So all of that type checks. Good. So what can we do with these different building blocks? Maybe I will, well, I can explain directly like that. I don't know if it's better if I type it or if I show you directly like this, but let me maybe just explain this code. So let me start with two helper functions that I define here. You have this case class vector with a size that is of type int that you've seen in the previous slide. And now I would like to be able to construct this precise type. Right now, this is not something that is included in Scala. So when you construct a vector with a precise value for a field, it will not infer the refinement type. Unfortunately, you have an issue about that. Therefore, currently, I have to define this helper here. Well, I have a precise constructor for my vector, and I say, okay, I will cast the result of the constructor to an instance of a vec where the field size has exactly the type of the argument. We have a similar problem for operation types. They are not correlated to term level operations right now. So if I want to write the result of an addition and have it typed with the type level operation plus, I also need a cast. So these are the two helper functions that I need here. And they are sufficient so that in the rest of the code, I don't need to cast anything. Of course, we would like to get rid of that, and I will come back to this later. But currently, we have to do that, which is, I think, a minimal effort because it's really the only helper function that we need, and then we don't need any cast. So what can I do with this? Then I have my class vector, and I define two mock functions, sum and concat. And the two functions impose restrictions on the parameters in the result. So here, this line might seem a bit odd at first. What does it say? It says that if I want to sum two vectors, so sum in the mathematical sense, they must have the same size. How do I write that? I say that the dat argument should have a precise size, which is the same as the outer vector. Okay. Why can't I just write size.type? Because if I do that, I will refer to this size that is here, the refinement. Okay, so I have to actually fully qualify it with vec.this.size, and it will actually refer to this size. Okay. Thanks to that, the compiler will be able to check that if I sum two vectors, well, they must have the same size that is known at compile time. You see here, because I have this helper function, everything is inferred. I don't need a precise return type here. This will return a vector of the precise size, which is the same as this size. Okay. Here is an example for concat. To concatenate two vector, I don't need to impose any restriction on the argument. I can concatenate any two vectors. However, by typing the result like that, then the compiler will know that what I return is a vector of size, the size of this plus the size of that. So what can I do with this? Well, I can say that I have a vector of size 6. I concatenate it with a vector of size 7. Therefore, the result will be a vector of size 13. And I can sum it with another vector of size 13. And this will all compile and return a vector of size 13. So this is all possible today. This works. If you look at the repo of the presentation, you have this example in particular. You can run it. Okay. So what is not possible today, as I said before, is to reason about abstract value, if you want. So these term references. So currently, if I want to say, well, if I add 2 times the type of m, it should be the same as 2 times m. Okay, and this requires some algebraic reasoning. And that's exactly my work, what I'm doing now. I'm implementing this in the compiler. And so I have a branch where all these examples work. So you can, this will basically group the terms in a sum together. Hence, if I have m plus m, it will be grouped to 2 times m. And it will also order them, so that they can be compared together. What can I do with this? I will now do a bit of live coding. So I will get this example here. So what about the time? Okay. I will just reuse this file here. Doesn't work because... Oh wait, yeah, probably. Actually, I will do that in my branch. Let me just... Okay, good. So here I'm in the code base because, of course, if I want to show you that, I will need my branch. I will take the example that I have. No, reuse this one. Okay, just retype it to show you. Okay, and so here I created a test that I want to be able to run. And I will run it by entering SVT. And let me show you the result of this. So I will just copy the path here. Okay. And I will print the result of the typer using this xprint typer. Good, so right now, if I have it like that,
Compiling the compiler.
yeah. It's actually an old branch, so every time I switch, it has to recompile like half of the compiler. Not sure if there is a way to speed this up.
Surprisingly, decorations work on the standalone file.
Yeah, they do. And I think if I over it, yeah, the size is not, the type is not exactly what I would like here, but I see that it actually has size 13.
If we can improve that, sure. We don't have that much test, I think, on structural types.
Yeah. Why is it so slow?
Because you chose Scala as your.
And you're sharing. It's always much slower when you're sharing.
Right. Yes, because it's way faster usually. Actually, okay. Yeah, that's right. Well, maybe we can already start to think about this. So, what I would like to do, well, I will first show you. If I have an abstract int, if you want, just give it this value. And now I have a vector of this size, and I concatenate it with another vector of the same size, then, as you understood, I'm able to type this as 2 times n type, if, of course.
So that's because it's using your branch of the compiler, right?
Exactly, yes. So this is not available yet, but this would work. Okay. So now let me try to encode a few other methods. So let's have the tail method that will return a vector which has a size. So I would need also precise type for that. So tail will return subtract size 1. Okay. If I prepend something, I will get a vector that has a higher size. It will be incremented by 1. So for this demo, let's just say that it's a vector of ints, but it could be, of course, a parametric type. Then let me also just.
But you don't use n in prepend.
No, so this would be a vector of int, and I would prepend an int, but it's not the size.
It's a value.
Yeah, okay. No. So it's it's more code. I'm not even sure it makes a lot of sense to write.
Okay.
Okay, and so this would maybe, so that we're not confused, let's say it's a vector of strings. Okay.
I have a dummy question. Can I ask it now?
Yeah.
I would like to know, why do you need sub? Why add with negative numbers, for instance, is not enough?
It might work. Let's try. So let's start with that, and then then we should try. Okay, so good. And now that I have this, my idea would be to type check a map method. So I will get a function, let's say a string to a string, and I will say that it returns another vector, well, equal to size. Oh, by the way, this finally compiled. So you can see that I was not lying about this one. And so it will, of course, return a vector of the same size. Okay. So how would I implement it? I will need an object, let's say a value that represents an empty vector. And I will say.
Well, you can also test if the size is 0.
Yes, I can, but you will see the problem with that. Okay, but that's okay. Let's do what you're saying. So let's say if this dot size equals 0, then
Can return this.
simply return this. Otherwise, these methods are not super. Maybe if I. Let's look at that. So then I should have the nice syntax, so I will map head, and then I will use tail, and I will also map resend. So I would like it to type check. Let's remove. Yeah, so exactly. You have a problem with this because this here is not precisely typed. So for this, you would need flow typing. You would need to say, okay, if I do a check where I know that the size is 0, then I should be able to.
But it's this.
It is, yeah.
Distance size has time factor distance size and time.
And if you use pattern matching, does it work?
It doesn't even matter that the size is 0. It should be the case for any size.
There is a bug for that.
So that's not flow typing.
Yeah.
It's just
type. Okay, so this is this bug.
Singleton type is not a subtype of a street.
So this is actually exactly the problem that we have. We have a type A, and then we type some value as a type of the field. We refine it, and it's not a subtype.
Yeah.
So I think if this bug is fixed,
then that should work.
then that would actually work.
Yeah.
Okay, but what is very nice, so okay, for now this doesn't work, so let's do it like that. But the rest works, and so
That assistance of without even an
so the type parameters is different. Yeah. So if I forget to type tail and I try to compile it again, I will have an error saying. Well, I expect a vector of size, but it has the size plus 1. Okay, and you can see the error message is actually pretty nice and understandable. So this requires algebraic reasoning. Why? Because I need to know that n.type plus 1 minus 1 is n.type. And with the constant folding that we currently have, this is not possible. Because it's not canceling terms. So if the operations were in the right order, maybe it could simplify plus 1 minus 1 to 0, but it would not cancel the term. So that's one of the things this branch does. Okay, so
if you do put back the tail dot, does it actually work?
yes, it does. I'm not
Yes,
sure.
it does.
Yeah.
It's pretty cool. It's horrifying, but it's pretty cool.
I think it's an exciting example because here we can actually type check a recurrence. So it's really the beginning of kind of formal verification at the type level. Okay.
Recurrence is induction in English. There's no such.
Yes, induction. Yeah. So maybe you're saying, well, there is still this as instance of it. It's a bit ugly, okay? But we can make it work today. So let's repeat our problem. We have we are actually checking a condition, and if this condition is true, we want a precise subtype. Does that ring a bell? Subtype reconstruction, GADTs, okay, yeah. So let me show you another example with GADTs. So we could, instead of refining the field as we did, define our vector class as a GADT that has two parameters, length and the type. And by the way, here, it works for parametric types as well. Then I have two cases here. I have the case nil, where the size is 0, and I type the type of the items with nothing, such that it can be a subtype of any type where the type parameter is not nothing. And I have the not nil case, where I just say it can be any int and any t here, okay? And then I can type my methods like that. So it's very similar to what we just did. The main change is that we're using these type variables instead of refinements. I did not write the implementations here, but we would need similar helpers to infer the precise type. So we would need to say, no, actually we would not even need a helper for the vector constructor, because it would infer the type parameter automatically. But we would still need it for the operations. And so this compiles today. Well, in my branch, of course, because you still need the algebraic reasoning so that the compiler knows that +1 - 1 is 0. But this works. Okay. There are tons of other problems if you use type parameters, but we don't see them in this example, unfortunately. Okay, and I think it's interesting because Alex, who developed GADTs in Scala, gave a talk 3 years ago, and he had exactly this example, and the only missing piece was this algebraic reasoning, and now it works. So you have the link here if you want to see the precise size. Okay, another real-world example, there is this tf.t library that gives precise types for tensors, TensorFlow tensors in Scala. And so here I have a very simple example. I have a tensor that has 2 dimensions, x and y, and I reshape it to a vector of size of dimension y and then x, so the dimensions are in different order. And the way it is implemented, why is it not opening the link? Oh, it crashed, okay.
Click on handling this hard.
Okay, this is the precise place.
Maybe increase the front. Oh, yeah.
Yeah. Oof. So when I reshape a tensor to a new tensor, I check using this implicit that I can reshape the old shape to the new shape. And what is can reshape? Well, it checks that the number of elements in old is the same as the number of elements in new. And how is num elements implemented? Well, it simply multiply the size of each dimension together. And so before, you would not have that x times y is equal to y times x, so this would not work. But with my branch, with my last changes, then this works. Okay? Good. I will not spend too much time on the problems now, but if you have questions about that later, it's still open. So there are reasons why the branch is not merged yet, of course. Okay, so let's come back to type level programming. Until now, we have seen a lot of operations on numbers, on integers, and I would like to show you what we can do with strings. So there is another building block that we need in order to really do type level programming, which are match types. So you all know what match types are. Basically, I can define this type here that checks if a string is empty. So it's also a type upper bounded by Boolean, but it actually has an implementation. And I will say, well, I match on the parameter. If it's the empty string, then it's true. Otherwise, it's false. The match types will be reduced, and it really allows you to implement some logic at the type level.
I have a question regarding match type because I'm not super familiar with them. What if we want to apply isEmpty of a value of type string, which is not a constant string? What happens here?
Yeah, so it will not be reduced.
So it's a compilation error.
No,
No.
it's not a compilation error. Well, here it will be at the time where we try to compare it with true.
Okay.
Okay, so during subtyping, it will say, well, I cannot say that this reduced to true because I cannot reduce it at all. So you will have actually a subtype error, and in the error message, you will have the information, a match type could not be reduced. Here is the one I could not reduce.
Okay.
Okay. So what can we do with this? We will implement a strongly typed printf in Scala. So you are all familiar with the printf function, I guess, in other languages. We would not need that in Scala because we have f strings, we have s strings, we have other things like that, but it made a nice, simple example. So what I would like to say is, well, if I pass this string with 2%d, then I expect 2 integers. Okay, how can I implement that? Well, I will need a match type that will use the type of the first argument to derive the type of the other arguments. And what is this match type? This is actually parsing of the string at the type level. So I have my main case here. So what I return is a tuple. So tuples are also strongly typed. So I will know exactly the type of each element of the tuple. So the base case is an empty tuple. And otherwise, I will simply match on the first character of the string. And if it's %, then if the following character is d, I will prepend the type int to my tuple and continue the recursion here. And if it's an s, so here it only works for strings and digits and decimals. And so if it's a string, I prepend the type string to my tuple of types. Does that make sense? Or am I going too fast?
Yeah.
Okay, good. And that works also because this will automatically be mapped to a tuple by the compiler. That's the last thing I need to say. So that also works today.
If you shouldn't write it like that, it's a bit confusing. Maybe you should write all the parentheses.
Yes, so I could, of course, I could have another pair of parentheses around here, and probably it would be clear. But it's another Scala feature that is useful in this case. So,
do you have to use 2-parameter list? No, just to use a trick of auto-tupling. Okay.
Yes, exactly. That's
Okay.
right. Yeah.
Or you could use a vec instead of a tuple, which is a thing you defined earlier.
Yeah.
But the vec is
Vec
homogeneous.
just has a size, so but we could define an H list that people
But
do.
tuples are H-lists,
But,
so why you?
Right. So this also compiles today. You have the example in the repo if you want to play with it. Okay. So Olivier, the author of match types, also made a library for strongly typed regexes, which use more or less the same ID. It's available here, and you can, thanks to this library, you can do that kind of things. You can type your regex, and then you will know that I expect exactly 3 parameters if I match this. So in this case, that will not compile because I actually tried to match with an additional parameter. So I encourage you to also have a look at this. Okay, so let's see how long do we have? Yeah, so I will not have time to do everything I wanted to do. So maybe let's skip the macro part. The main idea is I want to show you how we can implement new compile time operations. So my idea for a new operation would be, and maybe it's not a good idea, but the idea would be to have an operation read that is able to read the content of a file at compile time.
Wow.
So what will I have? I will have a read that takes a string argument and that returns a string. Okay. So why would I want to do that? Well, with this, I could say if I'm reading a CSV file, for example, or a JSON file, and I know exactly what file it is at compile time, then I could infer the precise result type. Okay. So let me show you how we could implement that in the team. So what I will do is that I will come back to the main branch. I will create a new branch. So I always use user interfaces. Okay, excellent. Now I can work. Good. So the first thing I want to do is to write a test. So tests for everything in .t are in the well-named test folder. There are different categories in this. Neg are the tests that should fail at compile time. And the one that we are interested in here is pause for the test that should compile successfully. So I will have a quick look at the list and see if there are already other tests that are named that are about compile time operation. And I see that, oh yes, there are already some tests about singletons here. So I will add a new test called singleton read.scala. Good. And because it is in this folder, it will be run automatically. So what do I expect here? I expect to be able to import scala.compiletime. Where can we put this? Maybe in string, ops.string, and I want to be able to import a read. Okay. And what I want to do is this. Well, I want to say if I read, for example, the content of, oh, sorry, I should have a test file here. Maybe it's not the best place to put it, but I will just add it here. Okay, good. And I will say that if I read this file, and this file will contain hello with a line break, then I should be able to assign the constant hello. Crazy, isn't it? How can we implement that? So first we need to add the read type in the library. So where are these? They are in the library folder where you have all the implementation of the library that is specific to Scala 3. And you have here a subfolder for compile time operations. And you have the string file. So we will add the type that we just defined before. So I will say this string, and it somehow returns string. Good. Now I should already be able to compile the first part of my tests. So the first line. Okay. Let's try this. Okay.
It needs to recompile the compiler.
Oh yes.
So maybe
Yeah, but
just start with the implementation and you will see the result of the compilation later.
Sure. So if I just do it like that, it will be a type alias, a type application like any other, and it will not have a special compiler support. Ooh la la. Okay, we'll probably have to recompile something.
Problem is incremental compilation.
Yeah. In general, if I recompile, then it works. Okay, so how can I add special?
To reload SBT, I think the ASM library version must be upgraded, so you need to reload SBT.
Oh, okay. So what I have here in terms of internal representation is a type application, an applied type. So where is this type defined? Let me just launch the compilation. All types, as you probably know by now, well, you of course, but the viewer, I guess, as well, are defined in types.scala at the top of the file.
10,000 lines.
Yeah, you have the full hierarchy of types, and what we are interested in here is applied type. And okay, this is this abstract class here. And what is important here is the normalize method. Try normalize to be more precise. So when you call normalized on a type, it will call this method. And if it returns no type, it will keep the same type. So this is the cases where we cannot normalize, and otherwise it will return the result. So what is normalization? Maybe I should start with this. It concerns all the types that we can somehow reduce. So right now, this is mainly match types and compile time operations. So it's the normalize method that will reduce match types, and it's the normalize method that will reduce constant fold compile time operations. So if you look at the normalized implementation for match types, you will see that they are reduced there. And here we are in applied type. So this is the place where we need to implement stuff for applications of type, like compile time operations. And you see this line here is important. It says I will try in the normalization process to constant fold it. So let's see what this function is doing. So it is cached, the result is cached on the run, so that when we reduce once an application, we don't have to recompute it all the time. But this is not very interesting code. This is just the caching. Where the magic is really happening is here in the type level class in try compile time constant fold. It was moved 2 days ago. So if you have never seen this type level class, it's normal. And so here I have all the magic. So I will match on my type and on the type I'm trying to apply here, tycon. And if this type is a compile time operation, I will not go into the details here, but I'm checking the symbol of the type. Then I will try to normalize it. And the core is here. So basically, it's a big chain of if the type I'm trying to apply is this, then I should fold like that. If it is this, I should fold like that, etc. So you see here all the operations that are on any. Then you have all the operations on int, all the operations on longs, etc. And what we are interested in here more specifically is the operations on strings. So we will need to add a case here for our read operation. It will look something like that. So first, there is no type name.read yet. Of course, we haven't defined it. So type name.charades.matches, etc. These are just constants for the name of the operations. So these are just strings. So I should add one for my read. So I come here to the standard names and I will add eval read.
Someone did not follow the,
Yeah.
the alphabetic order.
I'm following it. So maybe this should probably be at.
Oh, it's on string, so.
No, the names,
section,
they're in
yeah.
alphabetic
Ah.
order.
Ah,
Okay, and well, while I'm here, I could see for the substring case, for example, where is it used? And it can give me an indication or of what else I should change. And it's used in definitions.scala here. And here we define a set of all the operations on strings. This is used to identify compile time operations on strings. So I should also add my type here. And that's just the changes that are needed. Then I can come back here to my constant folding code. And I have an operation that takes a single argument. So you see you have some helper functions here. Basically what they do is that they check that both arguments are constant by recursively normalizing first. And if it's the case, then it will apply the second parameter. And there is one helper function for the case where I have a single argument, for the case where I have two, and for the case where I have three. So here I can use constant fold one. And I use my string value here. That is the argument. I matched it. Where did I match it? Oh yeah, no, actually it's a function that will try to reduce the argument as a constant and then try to cast it as a string. Okay, so what do I do in this case? I will do something very simple for demonstration purpose. That would probably not be a good real-world approach, but I will use scala.io.source.fromFile, use this argument, and make a string with it. So basically, it's just reading the whole file. That's the simplest way you have in Scala to read a file. For real-world implementation, we would probably reuse the T features, try to integrate with caching system, incremental compilations, etc., etc., etc. So this is not bulletproof, but this is for the demonstration. And I think I should have everything I need. So let me come back to my test, uncomment this, and see what happens. Suspense. Wow.
La, 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 la.
First time. First time.
If you use another constant, if you forget the O, for example, or whatever.
Fail. Found. Hello is wow.
Nice.
Right. Hello.
Horrible, but nice.
Yeah, so so it's open question where we should do that, of course. Is it really a job for compile time operations? Maybe not. We can achieve exactly the same thing with macro. I have an example in the repo of the presentation you can have a look at. It's not a full featured example, but it shows the building blocks that you need. Another alternative, if you have a schema somewhere, would just be to generate code and then to use it. That's probably the simplest and safest. Yeah, so of course, that was for the demonstration, but I think it was a fun example. Okay, so what time is it? Okay, I think I will stop here. So I will not go into details for the rest, for the macros, but yeah, good. Thank you very much.
Do you have any issues to recommend people to look at if they want to work in this area of the compiler, like type level operations?
So on purpose, I showed a simple example. So adding compile time operations is not super complicated, as you saw. It's 3 lines of code. Then the big parts of the problems are really in typer and how you can derive subtype between these operation types, especially when they are not reduced. So that's what I do with normalization. and reordering, etc. So that's the complicated part. Well, and then, yeah, there is subtyping in general. So this is not directly linked to operation types, for example, but this is a very important bug, as you saw before. It's a problem in practice. So this is, for example, an issue I would really like to be solved. So if people want to have a look at it, that would be nice. Yeah, no, I don't have a lot of other issues in mind.
Something that wasn't clear to me. So the example, the implementation you showed us, you did it in the main branch of the compiler. So we don't need your fork. Your branch is only needed for algebraic reasoning on types.
For numbers, yes.
Okay. And currently, is it possible to? So you say it's possible to implement the type read with macros. So it means it's possible to do it like outside of the compiler.
Yes.
Okay.
And it works today with macros. You can do that. It has been done in the past in real-world frameworks, and it was a disaster because on each keystroke you would reread some files. So there was this caching problem. So yeah, I would also not advise it to do it today with macros without a good caching system, of course, because if you reread the files that you need every time you recompute the type, then you have a big performance problem.
Wait. The file can change, so don't have a choice.
Yeah, but then you can imagine if you have, for example, you're reading a big GraphQL schema, maybe it's even on the internet, maybe you just cannot do 100 requests each keystroke. So
each save, not each keystroke, each save.
Yeah, so it depends if you are recompiling automatically.
You type check the file also at each keystroke. So
yeah,
that's already quite a big job. So
yeah,
reading another file, maybe it's not so much a problem.
If it's one file, I guess it's okay. As you saw here, it's. I think the problem is if you start to have this at different places and with a lot of files, which can happen for real-world schemas, right? If you have a GraphQL API, you will have actually hundreds of lines of schema, if not thousands. Yeah. So just to answer your question, why is it not?
Zero bug.
Oh no, I'm this is covered.
Basically, all the issues assigned to you.
Exactly. So if you want to have a look at issues that concern singletons, just look at all the issues that are assigned to. And
okay.
Be completely. Feel free to fix all of them. That should be with me.
Okay, bye.
Cool. Thanks.
Thank you. Any other question? Any point? Okay. So let's wrap up. Thank you very much.
Thank you.
Thanks.
Bye bye.